Right now, 100 billion photons pass through the top of your skull every second. The light reaching your eyes left our star 8 minutes ago, but the photon itself experienced zero time on that journey. Zero. Emission and absorption are the same instant for every photon that has ever existed. We are going to watch a single photon pass through two places at once, see a Nobel Prize prove that reality has no fixed state before you look, and trace the invisible photons that hold all matter together. Like and subscribe if you want to keep going, because we are still not done being wrong about light. Prepare yourself, we begin. Right now, something extraordinary is happening to your body that you have never once thought to question. Every second, 100 billion photons pass through the top of your skull. They stream through bone and tissue without pausing, carrying the warmth of our star across 93 million miles of empty space, arriving at the nerve endings in the back of your eyes and firing patterns that become the experience of seeing the world. They carry the color of the sky, the brightness of a lamp across the room, the face of someone you love, and in all the time you have spent moving through a world made visible by light, there is a very good chance you have never once asked what light actually is. That question turns out to be one of the most unsettling in all of science. The photon that just entered your eye was born inside the core of our star roughly 10 million years ago. The energy that eventually drove it was produced in a nuclear fusion reaction deep in the star's center, and from there it began an absurdly slow crawl toward the surface. The inside of a star is so impossibly dense that a photon can only travel a tiny fraction of an inch before something absorbs it and something else re-emits it in a random direction. It bounces and scatters outward, step by random step, for somewhere between 10 million and 100 million years. By the time it reaches the outer layers of our star and finally escapes into open space, the civilization that will eventually build telescopes to study it has not yet evolved. The dinosaurs are still millions of years from extinction when some of those photons break free. And then the photon crosses 93 million miles of empty space in 8 minutes. Your brain turns what arrives into vision, warmth, color, and shadow. You have been doing this every moment of your waking life, and the process feels so natural that it vanishes. Light is just there. It has always been there. But here is the thing that physics will not let you ignore once you know it. We cannot tell you what a photon is. Physics has mapped the structure of atoms, explained the birth of galaxies, predicted the existence of gravitational waves decades before instruments could detect them. The equations describing how photons behave are so precise that the agreement between theory and measurement stretches to 12 decimal places, a level of accuracy with no parallel in any other science. And still, what a photon actually is, at the most fundamental level, is a question that remains genuinely, stubbornly open. Every honest physicist will say the same thing. We know what photons do. We have no clean answer for what they are. That is not modesty. It is a confession, and a strange one, because light is the thing we use to understand everything else. We use photons to see, to communicate, to probe the structure of matter and the shape of the cosmos. The instrument is the mystery. How did we get here? The story starts long before telescopes or equations, in a world where some of the sharpest minds in history looked at light and reached for answers with complete confidence. They were wrong. And then they were wrong again. And the path from that first wrong answer to where physics stands today is one of the most spectacular intellectual journeys the human species has ever taken. It begins, appropriately enough, with a question about the eye. For most of human history, the most basic fact about light was contested. Does it travel from an object to the eye, or does it shoot outward from the eye itself to sense the world? Ancient Greek philosophers argued both sides with equal conviction. Euclid and Ptolemy believed that visual rays emanated from the eye, scanning the world the way fingers reach into darkness to feel what is there. Aristotle disagreed. The debate ran for centuries without resolution, and the men conducting it were doing sophisticated geometry and building lasting traditions of inquiry. They simply had the direction of light traveling backward. The person who ended that particular argument worked in Cairo around the year 1000. A scholar named Ibn al-Haytham conducted the first systematic experiments on optics, placed a box with a small hole in one wall, let light project an inverted image of the outside world onto the opposite interior wall, and wrote it all down in a book that would eventually reach Europe and reshape how educated people thought about vision. Light enters the eye. It arrives from elsewhere. The eye receives. That much was now settled. But what light actually was remained wide open. Descartes, in the 17th century, imagined light as a kind of pressure transmitted instantly through a medium that filled all of space. He was wrong about the medium, wrong about the speed, and wrong about the mechanism, but his attempt to give light a mechanical explanation was a step in the direction physics was headed. The next step required actually measuring how fast light moved. In 1676, a Danish astronomer named Ole Rømer was watching the moons of Jupiter through a telescope and noticed something that no one had explained. The timing of the moon, Io's eclipses behind Jupiter, varied depending on where Earth was in its own orbit. When Earth was moving toward Jupiter, the eclipses arrived slightly early. When Earth was moving away, they arrived slightly late. Rømer understood what he was seeing. The delays were caused by the time it took light to travel the extra distance. For the first time, a human being had evidence that light traveled at a finite speed and could even estimate what that speed was. The estimate was rough but astonishing. Light crossed the distance from Earth to our star in about 11 minutes. By his calculation, the modern measurement is 8 minutes and 20 seconds, so he was close. Still, this told no one what light was made of. It told them how fast something moved. The question of whether that something was a wave or a collection of particles had not yet been answered, and the two competing ideas were already circling each other. One of the two camps was about to receive the most powerful endorsement a scientific idea can get. The greatest physicist of the age was about to pick a side. Isaac Newton spent years turning light apart in a darkened room. He cut a small hole in a window shutter, let a narrow shaft of light through, and held a glass prism in the beam. What came out the other side was not white light stretched thin. It was every color laid out in sequence. Red curving one way, violet another, the full visible spectrum spread across the wall like a map of something hidden inside daylight. Newton understood immediately that white light was a mixture, that colors were components, and that the prism was sorting them by their different behaviors in glass. He explained all of it with particles. In his book, Optics, published in 1704, after years of deliberate delay, Newton laid out a theory of light as a stream of tiny corpuscles, fast-moving particles that flew from a source in straight lines. Reflection was simply the corpuscles bouncing off a surface like tiny balls off a hard floor. Refraction, the bending of light as it passed from air to glass, happened because the particles were attracted toward the denser medium and accelerated. Different colored particles had different masses and interacted with surfaces differently, which is why prisms sorted them. The whole picture was neat, mechanical, and consistent with everything Newton had seen. His authority was enormous. By the time optics appeared, Newton had already published the Principia, had already invented calculus, had already given the world a theory of gravity so powerful that it could predict the motion of planets. When he said light was made of particles, the scientific world listened. A competing theory had been proposed decades earlier by Christian Huygens, a Dutch physicist who argued that light was a wave spreading outward through space the way ripples spread across water. Huygens had mathematics to support it. He had experimental observations. He had everything except Newton's prestige. Against the weight of Newton's name, the wave theory retreated into the background. For a century, corpuscles ruled, but there was one phenomenon that Newton's model handled awkwardly, and it did not go away. Light bends around the edges of objects. The sharp geometric shadow that particles would cast, hard-edged and crisp, is never quite what you actually see. At the boundary between light and shadow, there is always a slight blurring, a faint spreading of the beam as if it were curling around the obstacle. Particles cannot do that. Particles fly in straight lines. If corpuscles hit the edge of a barrier, they should either pass or stop. Newton's model had no good answer for this. His followers worked around it. His prestige kept the wave theory suppressed for longer than it deserved, but a question that cannot be answered has a way of surviving. In the early 1800s, a British physician and polymath sat down with a simple piece of equipment and built the case against Newton so cleanly that the entire scientific establishment could no longer ignore it. The experiment required nothing more than a card, 2 tiny holes, and a light source. Thomas Young did not set out to overturn the greatest scientific mind of his era. He set out to understand something he had noticed about patterns of light and shadow. In 1801, he arranged an experiment that would become one of the most important in the history of physics. He took a thin card with 2 narrow slits cut close together, shone light through both at once, and watched what appeared on the screen behind them. The screen showed something impossible, at least by Newton's logic. Where 2 beams of light overlapped, the expected result was more light. Twice the particles, twice the brightness. Instead, Young saw alternating bands, bright stripes where the light was intense, and between them, dark stripes where no light fell at all. 2 beams of light had produced darkness. The places where the most light should have fallen showed the least. This is exactly what happens when 2 waves meet and cancel each other. If the crest of one wave lines up with the trough of another, they annihilate. The result is silence, or in this case, darkness. Particles cannot do this. Particles add. 2 streams of particles colliding at the same point produce more particles, never fewer. The only thing that produces this pattern of constructive and destructive interference is a wave. And there was worse still for Newton's model. The dark bands, the places where 2 beams of light produced 0 light, could only be explained if the 2 beams were traveling as waves with a precise phase relationship, which meant light was spreading out as it passed through each slit, bending around the edges, propagating in all directions the way a water wave radiates outward from a disturbance. This was the very bending around corners that Newton's corpuscles could not do. Newton had been wrong. Young published his results and was largely ignored, then attacked. Newton's shadow stretched long enough that the British scientific establishment initially resisted. A critical review accused Young of undermining everything Newton had built. But the experimental result did not go away. Other physicists repeated it and extended it. A French engineer named Augustin-Jean Fresnel developed a full mathematical theory of light as a wave that predicted new phenomena, made testable predictions, and proved correct every time. By the 1820s, the wave theory was ascendant, and Newton's corpuscles were finished. Light was a wave. The experiment had proven it. But the experiment had raised a deeper question that no one had answered. Waves need something to wave in. Ocean waves are disturbances in water. Sound waves are pressure variations in air. When you strip away the medium, there is no wave. So if light is a wave spreading through space, what is it a wave of? What is rippling? What is oscillating as the light travels from our star to the surface of the Earth? For decades, the only answer physicists could offer was a placeholder. They called the medium the luminiferous ether, an invisible substance filling all of space through which light vibrated. No one had ever detected it. No one could describe what it was made of. It was a name for ignorance, dressed up as an explanation. The real answer was waiting in a set of equations, and it was stranger than anyone expected. James Clerk Maxwell was working on a problem in electromagnetism in the early 1860s when he made a discovery that changed physics as permanently as Newton's gravity had. He was not thinking about light. He was thinking about how electric fields and magnetic fields relate to each other, trying to put the scattered experimental laws of electromagnetism into a consistent mathematical form. The equations he assembled described how a changing electric field creates a magnetic field, and how a changing magnetic field creates an electric field. Each drives the other in a cycle. Maxwell noticed that if you set these two fields oscillating together, the equations predicted that the combined disturbance would propagate through space as a wave. He calculated the speed of that wave using the known constants of electricity and magnetism, and the number he got was 300 million meters per second. He already knew that number. It was the speed of light. Maxwell wrote, in a paper published in 1865, that light is an electromagnetic disturbance propagated through the electromagnetic field. It is a wave in the electric and magnetic fields themselves. The fields are the medium. There is no invisible substance required. Two fields that exist throughout all of space ripple against each other in a rhythm, and that rhythm is what we see when we open our eyes in the morning. The confirmation came from a laboratory in Germany more than 20 years later. A physicist named Heinrich Hertz built an apparatus that created oscillating electric sparks. Across the room, another device detected the spark through empty air at the same frequency. Hertz had produced and received radio waves, invisible waves of oscillating electromagnetic field that traveled at the speed of light because they were, fundamentally, the same thing as light, just at a different frequency. Color, it turned out, was nothing more than the frequency at which a photon's fields oscillated. Radio waves, visible light, X-rays, and gamma rays were all the same phenomenon at different pitches. Maxwell's theory was a triumph of the highest order. It unified three phenomena that had seemed separate, derived the speed of light from first principles, and predicted the existence of radio waves before anyone had detected them. Physics had its wave theory on solid ground. For exactly 35 years, that ground held. Then experimenters started asking what should have been a simple question. When you heat a piece of metal until it glows, what colors does it emit and why? The answer the wave theory gave was not just wrong, it was catastrophic. Blackbody radiation sounds like a technical detail. It is actually the fault line where classical physics shattered. A blackbody is any object that absorbs all the light that falls on it and radiates energy purely as a function of its temperature. A glowing piece of iron in a furnace is a reasonable approximation. As the temperature rises, the iron goes from dull red to orange to yellow-white, and the peak of that glow shifts toward higher frequencies as it gets hotter. Classical wave theory could explain this shift in peak color well enough at low frequencies. At high frequencies, something went violently wrong. The problem was in the mathematics. Classical physics described light as a continuous wave and predicted that a heated object would radiate energy across all frequencies simultaneously. When physicists calculated how much energy a blackbody should emit at short wavelengths, high frequencies, ultraviolet and beyond, the math gave them infinity. The object should pour out infinite energy at every frequency above a certain threshold. Every heated object in the universe should instantly flood space with limitless radiation. The chair you are sitting in should be glowing with impossible brightness. Everything should be. This result was called the ultraviolet catastrophe, and it was not a minor discrepancy or an approximation that needed refinement. It was a prediction that, if taken at face value, implied the universe could not function. Physics had a wave equation that matched experiment beautifully for some frequencies and predicted infinite disaster for others, and no one could find the mistake. For most of the 1800s, physicists tried to patch the theory. They adjusted constants. They added terms to the equations. Every attempt that fixed the problem at high frequencies broke the prediction at low frequencies. No single equation could fit the whole curve. The catastrophe had no solution within the framework that Maxwell's beautiful theory had provided. By 1900, two German physicists, Wilhelm Wien and Lord Rayleigh, had each derived equations that worked in different halves of the spectrum and failed completely in the other half. The right answer had to lie somewhere between them, but nothing in classical physics pointed toward where. A physicist in Berlin had been staring at this problem for years and was growing desperate. He had tried everything the existing framework could offer, and none of it worked. So he tried something that should not have worked. He introduced an assumption so bizarre, so philosophically repugnant to everything physics had built over 2 centuries, that he considered it a temporary mathematical trick rather than a description of physical reality. It was not a trick. Max Planck announced his solution in December of 1900 at a meeting in Berlin, and he genuinely believed he was being sly. The assumption he had made to fix the blackbody curve was so radical that he fully expected it to be replaced once someone found the real explanation. He would spend years afterward trying to undo what he had done, trying to fold his strange new assumption back into classical physics. He could not. The assumption was correct, and what it implied was permanent. Planck's trick was this. Classical physics assumed that a heated object could emit electromagnetic energy in any amount, the way a tap can release any quantity of water. Planck assumed instead that energy could only be emitted in discrete chunks, packets of a fixed size, each chunk proportional to the frequency of the radiation being emitted. He called these packets quanta, from the Latin for how much, and he gave the proportionality constant a name, h, Planck's constant, a number so small that in everyday life its discreteness is entirely invisible, but at the scale of atoms and light, it governs everything. The equation was simple. Energy equals h times frequency. Low-frequency radiation, long wavelengths like radio waves, carries quanta of very small energy. High-frequency radiation, ultraviolet and beyond, carries quanta of very large energy. At high frequencies, the quanta are so expensive in energy terms that the thermal jostling inside a material cannot produce many of them. The catastrophe disappears. The blackbody curve fits perfectly across all frequencies with a single equation. Planck published the fit. He downplayed the assumption, but the assumption had consequences that could not be contained. If energy in electromagnetic radiation only comes in discrete packets, then at some fundamental level, light is granular. The smoothness, the continuity that Maxwell's wave theory required, was an approximation. At small enough scales, the wave broke into pieces. The number itself is almost unfathomably small. Written out, Planck's constant is about 6.6 times 10 to the negative 34th joule-seconds. In everyday life, energy appears smooth because the steps between quanta are too tiny to detect. You would need to count individual grains of sand on a beach that stretches to the horizon. That is the ratio between the energy you use lifting a coffee cup and the energy of a single quantum of visible light. The granularity is there, in everything, all the time. We simply cannot feel it at our scale. Planck spent years insisting this was a mathematical bookkeeping device and nothing more. He told anyone who would listen that the real physics was still continuous. He was hoping someone would rescue him from the implication of his own equation. 5 years later, a young patent clerk in Bern decided that Planck was not being nearly radical enough. Albert Einstein was 26 years old in 1905 when he published 4 papers that each, individually, would have been sufficient to make a career. The one that won him the Nobel Prize was not the one about relativity, it was the one about light. Einstein read Planck's solution to the blackbody problem and drew the conclusion that Planck had refused to draw. If electromagnetic energy can only be emitted in discrete packets, then perhaps light itself travels in discrete packets. The quantization runs deeper than the emission process. It lives in the nature of light as it moves through space. Light itself, Einstein proposed, is a stream of individual energy packets, each one carrying energy proportional to its frequency. He used this idea to explain something that had been puzzling experimenters for years. When light shines on certain metals, electrons fly off the surface, the photoelectric effect. Classical wave theory predicted that the energy of those ejected electrons should depend on the brightness of the light, more intense light, delivering more energy to the electrons it struck. Experiments showed something different. The energy of the ejected electrons depended entirely on the frequency of the light, not its brightness. Dim violet light ejected electrons with far more energy than bright red light. Bright red light below a certain frequency ejected no electrons at all, regardless of how intense it was. Doubling the brightness of the wrong-colored light did nothing. Einstein's explanation was exact. Each electron is struck by a single packet of light. The packet's energy is fixed by its frequency. If the packet does not carry enough energy to knock the electron free, no amount of additional low-energy packets will help, because no single one of them can do the job alone. The threshold exists because the ejection requires a minimum energy, and only packets above a certain frequency carry that much. The mathematics fit every experimental measurement with perfect precision. The wave theory of light, confirmed so thoroughly by Young's double slit and Maxwell's equations, had now been contradicted by light itself. Light arriving at a metal surface did not behave as a wave distributing energy smoothly across the surface. It behaved as a stream of particles, each striking a single electron in a single discrete event. The physics community largely accepted the math and rejected the interpretation. Planck himself voted against awarding Einstein a prize for it. Even those who admired Einstein's result could not bring themselves to believe that light was really made of particles again. Young's interference experiment had ended that argument 100 years earlier. Or so they thought. A physicist in Street Louis was about to make the discomfort much worse. Robert Millikan was one of the most careful experimenters of his generation, and he spent more than a decade trying to prove Einstein wrong about the photoelectric effect. He was not trying to save classical physics out of stubbornness. He was a rigorous scientist who looked at Einstein's claim that light was made of particles and thought the idea was physically absurd. The wave theory had too much experimental support. Einstein had to be wrong. Millikan built the most precise apparatus the problem had ever seen. He cleaned his metal surfaces in a vacuum to remove contamination. He varied the frequency of the light with precision and measured the energies of ejected electrons across a wide range. He repeated the measurements until his data was as clean as experiments got. He was looking for a discrepancy, a place where the measurements broke from Einstein's predictions. He expected one. His entire experimental program was built on the assumption that one existed. He did not find one. By 1916, Millikan had confirmed Einstein's photoelectric equation to an accuracy that left no room for doubt. The relationship between frequency and electron energy was exactly as Einstein had calculated, straight to the decimal place. The threshold frequencies existed exactly where Einstein said they would. Everything worked. The equation was right. Millikan published the results and then wrote in the same paper that he did not believe the theoretical explanation behind them. The equation fit the data, he said, but the idea of light as discrete particles was still physically untenable. He had handed Einstein the Nobel Prize and simultaneously refused to accept what it meant. He was not alone. Bohr resisted. Planck resisted. Even the greatest experimenters can confirm a result without accepting what it implies. The entire generation that had been trained on Maxwell's electromagnetic waves could not quite let go. They accepted the numbers and rejected the picture. This is more common in physics than the history books suggest. Sometimes an equation runs ahead of the understanding, and the people doing the measuring know the equation is right before they know what it means. The evidence piles up on one side of the room, and the physicists stand on the other, waiting for an interpretation that never arrives. What it meant was this: if light travels as discrete packets of energy, and each packet acts like a projectile striking individual electrons, then those packets carry something more than energy. The collision between a light quantum and an electron involves a transfer of motion. Motion requires momentum. If photons have energy, they must have momentum. That question was about to be answered with X-rays and a block of graphite. In 1923, a physicist in St. Louis named Arthur Compton aimed a beam of X-rays at a piece of graphite and changed what scientists meant by the word light. X-rays are electromagnetic radiation, light at a very high frequency, carrying far more energy per quantum than visible light. Compton fired a controlled, monochromatic beam at the carbon in the graphite block and collected the X-rays that scattered off it. When he measured the scattered radiation, he found something that the wave theory of light could not explain. The scattered X-rays had a longer wavelength than the original beam. The light had lost energy in the collision. Waves do not do this. A water wave bouncing off a wall comes back at the same frequency it went in. A wave scattering off an obstacle does not slow down. Maxwell's electromagnetic waves should have scattered off the electrons in the graphite and come back at the same frequency they entered. The electrons should have absorbed and re-emitted the radiation without any change in wavelength. Compton treated the X-ray quantum as a particle. He wrote out the relativistic collision equations. A photon with momentum equal to its energy, divided by the speed of light, striking an electron at rest, transferring some of its momentum to the electron and recoiling with less energy. The mathematics of a billiard ball collision. The formula that came out predicted exactly how much the wavelength should shift depending on the angle of scattering. It matched the data precisely. Shortly after, Charles Wilson's cloud chamber photographs showed the recoiling electrons themselves curving away from the collision points at exactly the angles the calculation predicted. The electron tracks were visible. The collision was real. Photons carry momentum, and when they hit electrons, the transfer is governed by exactly the same conservation laws that govern balls striking balls. The wave picture of light had no explanation for this. The particle picture explained it completely, and yet Young's double-slit experiment was still right. The interference patterns still appeared. Both things were true at the same time, and no one had a framework that made sense of both. Light behaved as a wave when it spread through slits. Light behaved as a particle when it struck electrons. The experiment determined the answer, and the two answers were contradictory. Physics now had a name for this contradiction. It had a formula for it. It did not have an explanation. The word for the thing that carried this contradiction was about to be coined, and it would come from an unexpected direction. The word photon did not come from Einstein, who introduced the particle of light to physics. It did not come from Compton, who proved it carried momentum. It came from a chemist at the University of California, Berkeley, named Gilbert Lewis, who published a short letter in the journal Nature in December of 1926. Lewis was working on a theory of light in which energy was carried between atoms by permanent, indestructible particles that he wanted to name. He proposed the word photon, from the Greek word for light, phos. Lewis's specific theory did not survive. His particle was not quite the same thing that Einstein and Compton had been describing. The permanent, indestructible carriers he imagined do not match the photons that quantum mechanics later codified, which can be created and destroyed freely. But the word was perfect. It was compact, memorable, and rooted in ancient Greek. Arthur Compton adopted it in 1928. Within a few years, every physics textbook printed the word as standard vocabulary. The naming of the photon felt like a resolution. A century of argument had landed on a single syllable. Physics had identified its object, given it a word, measured its energy and its momentum. It had a formula for how its energy related to its frequency, confirmed to extraordinary precision by two separate Nobel Prize-winning experiments. The photon was real, and yet the scientists who had done the most to establish it were deeply uncomfortable with what they had found. Einstein himself said near the end of his life, in words that have never stopped being true, that every fool thinks they know what a photon is, and every fool is wrong. He had introduced the photon to science in 1905, spent decades working with quantum theory, and died in 1955 still without a satisfying picture of what a photon actually is when it is not being measured. Planck had hoped his quanta were a temporary convenience. They were not. Millikan had proven Einstein's equation while refusing to accept the physical picture. That picture kept imposing itself. Bohr built an entire philosophy around refusing to ask what a quantum object was doing between measurements. He called it complementarity, and it became the dominant interpretation in physics for the rest of the 20th century. That philosophy held for decades, which tells you something about how uncomfortable the alternative was. The photon had a name. It had equations. It had 2 Nobel Prizes pointing at it. What it did not yet have was an explanation for the experiment that would come next, because in the years after Compton's graphite block and Lewis's letter, physicists began asking a very specific question, not about beams of light, about single photons, one at a time, sent alone through the apparatus that Young had used to end Newton's corpuscle theory. 1 photon, 2 slits, the interference pattern that requires a wave, a single point of light arriving at the detector, like a particle, hundreds of single points accumulating into the striped pattern that only waves can produce. What they found broke the framework entirely, and it has never been repaired. The setup was as simple as science gets. 1 light source, 1 barrier with 2 slits, 1 screen to catch whatever came through. In 1901, Thomas Young had used this arrangement to prove Newton wrong, to show that light spread as waves and produced interference fringes that particles could never make. A century later, experimenters were still sitting in front of the same basic apparatus, but they had modified it in one critical way. They had turned the light down until only 1 photon at a time was in flight. The first version of this experiment required more patience than drama. In 1909, a Cambridge physicist named G.I. Taylor, encouraged by J.J. Thomson, who had discovered the electron, set up a double-slit apparatus with a light source so faint that on average less than 1 photon was present in the entire device at any moment. Then he waited. He left the photographic plate exposed for 3 months, collecting photons one at a time, each one landing individually, building up a record of where light had arrived. When he developed the plate, the interference fringes were there, the same alternating bands of bright and dark that Young had seen with a full beam of light, the same pattern that required waves. Each photon had arrived as a single point, a single click, a single grain darkened on the film, and yet over 3 months and millions of individual photons, those points had arranged themselves into a wave pattern. There is no way to make sense of this with ordinary intuition. Each photon traveled alone. There was nothing for it to interfere with. A particle fired through a single slit should land somewhere behind that slit and not behind the other one. A particle has no mechanism to know the other slit exists. And yet, the accumulating pattern showed that photons were avoiding the dark fringes and clustering in the bright ones, as if each photon somehow registered both slits and chose its landing point accordingly. Modern versions of this experiment use detectors sensitive enough to register a single photon in real time, confirming the same result with complete precision. Fire them one at a time, and the first arrivals look random. Then patterns begin to emerge. By the time thousands have landed, the interference fringes are unmistakable. The photon, traveling as a solitary quantum, produces an interference pattern that only makes sense if it passed through both slits simultaneously. That phrase sounds like a mistake. It is the actual result of the experiment. The formal language of quantum mechanics calls it superposition. The photon exists as a combination of the path through the left slit and the path through the right slit at the same time. And these 2 possibilities interfere with each other the way waves interfere, building up in some places and cancelling in others. The mathematics is clean. The physical picture remains stubbornly beyond ordinary visualization. But the strangest part is not the interference. The strangest part is what happens when you try to resolve the mystery by watching more carefully. Place a detector at 1 slit, sensitive enough to register a photon passing by without absorbing it. Make it as gentle as possible. Tell yourself you are only gathering information. The interference pattern vanishes. disappears completely. The alternating bright and dark bands collapse into two bright patches directly behind each slit, exactly the pattern you would expect from particles going through one or the other. The photons have stopped behaving like waves, change nothing about the light source, change nothing about the slits. Add only the detector, and the physics transforms. The immediate instinct is to blame disturbance. Perhaps the detector jostles the photon, knocking it off its wave-like path. Even a gentle measurement requires some interaction, and maybe that interaction is enough to disrupt the delicate quantum superposition. This explanation sounds reasonable, and for a while it satisfied most physicists. You are disturbing the photon in the act of looking. Then experimenters started testing whether the disturbance explanation actually held. What they found was that the interference pattern did not depend on how much the measurement disturbed the photon. It depended entirely on whether which path information existed at all. Even when the detector at the slit interacted with the photon so gently that it transferred almost no energy, the interference vanished. Even when the measurement device was arranged in a way that could, in principle, tell which slit the photon went through, but the readout was left unexamined and unplugged, the interference still vanished. The data was never read, no conscious being ever checked the result, and still the pattern disappeared. That result takes a moment to absorb. The interference is not destroyed by the act of looking. It is destroyed by the existence of information about which path was taken, regardless of whether anyone ever accesses it. The universe appears to be sensitive to whether the information exists somewhere in the physical world. Push it further still, and things become more uncomfortable. Set up the detector so that it will record which path information, then physically destroy the record before anyone could look at it. The interference is still gone. As long as the measurement device interacted with the photon in a way that left any physical trace anywhere pointing to which slit it took, the interference collapses. Physicists call this decoherence. When the photon's quantum state becomes entangled with the measuring device, even in the tiniest way, the two possible paths stop being able to interfere with each other. Interference requires the two paths to remain isolated, unentangled with anything else. The moment the outside world gains access to the path information, that isolation breaks. This is deeply unsettling for a specific reason. The interference pattern is not a property of the photon alone. It is a property of the entire experimental situation, including whether the rest of the universe has access to the path information. Change the experimental context, and the photon changes its behavior across the whole apparatus instantly. The photon was already heading toward the detector before it reached the slit. And whether it lands as part of a wave pattern or as part of a particle pattern depends on what happens at the slit after it leaves the source. That leaves a question no one could easily dismiss. If the photon adjusts its behavior to match the measurement context, does it have a definite path before the measurement at all? Or does the path only come into existence when the measurement forces a choice? This is the question that split physicists into camps that have not fully reconciled since. Niels Bohr had an answer, and it was more philosophically radical than anything Newton or Maxwell had ever proposed. His answer was that asking which the photon really is, a wave or a particle, is the wrong question. The two descriptions are not two theories competing to describe the same underlying reality. They are two mutually exclusive experimental contexts, each giving complete results in its own domain, each making the other impossible to observe simultaneously. Bohr called this principle complementarity, and he spent years insisting it was not a limitation of our measurements but a structural feature of nature itself. When you set up an experiment to see interference, you will see interference. When you set up an experiment to see which path the photon took, you will see a definite path. The two setups are mutually exclusive. The question of what the photon really was, while you were not measuring it, simply has no answer, because there is no such reality to describe. Werner Heisenberg made this concrete with his uncertainty principle, which connects to duality in a precise way. The more closely you pin down where a particle is, the less you can know about how it is moving. These are not limitations of instruments. They are limits baked into the structure of quantum mechanics itself. Asking for wave behavior and particle behavior simultaneously is asking for a complete experiment and its opposite to run at the same moment. The Copenhagen interpretation, as this cluster of ideas came to be called, was enormously practical. It gave physicists a set of rules for making predictions, for calculating where photons would land and how electrons would behave, without requiring anyone to have a picture of what was happening between observations. It worked. It produced numbers that matched experiment to extraordinary precision. It built the foundations of modern electronics, lasers, and every quantum technology that followed, but it left a deep unease. Copenhagen drew a hard line between the quantum world, described by wave functions and probabilities, and the classical world of measuring devices and observers. "Do not ask what is happening on the quantum side between measurements," Bohr said. "That question has no answer. The act of measurement is where the quantum becomes definite." For many physicists, this felt like abandoning the ambition of science itself. Physics had always tried to describe what the world is doing, not merely what we observe it doing. Copenhagen said the two might be permanently different things. Einstein could not accept this. He spent decades arguing that quantum mechanics must be incomplete, that some deeper theory must exist in which particles have definite positions and definite states, whether or not anyone looks. But every time someone proposed a more complete picture, it ran into the same wall. Every experiment confirmed the quantum predictions exactly. Every attempt to smuggle definite underlying reality back into the theory produced contradictions with those results. The photon seemed to demand that questions about its nature only have meaning when measurements are made. But what exactly counts as a measurement? That question turned out to be harder than anyone anticipated. And then, in 1982, a physicist asked whether you could take back a measurement after you had made it. Marlon Scully was a physicist who, in 1982, asked what seemed like a paradoxical question. You run the double-slit experiment with a detector that marks each photon to show which slit it went through. The interference disappears. What if you erased the mark? The question was precise and experimentally serious. If which path information destroys interference, and erasing that information restores quantum coherence, then erasing it should bring the interference back. But that raised an immediate problem. By the time you erase the mark, the photon has already landed on the detector screen. The result is in the past. Whether the interference pattern appeared or not has already been recorded. Can erasing information that no longer matters change something that has already happened? The setup Scully and his collaborator proposed used pairs of entangled photons. When a photon passes through the double slit, it creates a partner photon linked to it by entanglement. The partner carries the which path information. The original photon lands on the screen. A second detector captures the partner and can either preserve the which path information or erase it, depending on the setup. Look only at the screen photons, and you see no interference. There is no pattern, but sort those screen results by what happened to their partner photons, and a different picture emerges. Screen photons whose partners landed on detectors that preserved which path information show no interference. Screen photons whose partners landed on detectors that erased which path information do show interference. When those subsets are separated out and compared, the interference is real. Erasing the information brings it back, even though the screen photon has already been detected. Here is the precision that matters. You cannot use this to send a signal backward through time. The two subsets, the ones showing interference and the ones not showing it, are completely scrambled together at the screen and look like random noise until you already know which partner photon went where. Only when you compare both halves of the data, after the fact, do the patterns emerge. The interference is hidden in the correlations. This is not a loophole. It is a deep fact about quantum mechanics. Information about which path status is not simply present or absent at the photon. It is distributed across the full entangled system. You can choose, after the fact, to extract that information or to destroy it, and the behavior you recover at the screen changes accordingly. A later version of the experiment pushed this even further. The partner photon was sent down a much longer path before being measured, so the decision about whether to erase or preserve which path information happened after the screen photon had already landed. The partner's measurement was not completed until after the event it supposedly influenced. And still the correlations matched the quantum predictions perfectly. The past, it seemed, was not fully written until the future had decided what to record. Wheeler had predicted something like this, but on a scale that made the laboratory version seem modest. John Wheeler was one of the most creative physicists of the 20th century. The man who coined the term black hole and spent decades pushing quantum mechanics to its most extreme logical limits. In 1978, he published a thought experiment that made the quantum eraser look conservative. The setup borrowed from standard interferometer experiments. A device that splits a beam of light into two paths, lets them travel separately, and then recombines them to produce interference. You can run this in two ways. Close the recombiner and let the paths meet, and the photon produces an interference pattern. Open the recombiner so that each path leads to a separate detector, and the photon lands on one detector or the other, telling you which path it took. Wave behavior or particle behavior, you choose. Wheeler asked, what if you wait until the photon has already entered the interferometer before you decide? The photon leaves the source. It hits the first beam splitter and enters the device. While the photon is already in transit, you make the choice. Close the recombiner or open it. The decision comes after the photon has committed to being inside the apparatus. If quantum mechanics was right, the photon would behave as if it already knew which version of the experiment you were running, even though your choice came after it entered the device. Wave behavior if you chose interference. Particle behavior if you chose path detection. The photon would retroactively decide what kind of thing to be based on a decision made after it was already in flight. Laboratories tested this. The experiments used random number generators to switch the measurement setting while the photon was already traveling through the interferometer, switching in a time shorter than it would take any signal, even one at the speed of light, to travel from the switch back to the photon. Wheeler's prediction was confirmed every time. The photon complied with the choice made after it had entered the device. The careful interpretation says no information is traveling backward in time. Quantum mechanics says the photon does not have a definite trajectory until measured. There was never a definite prior state to retroactively adjust. The measurement creates the definite outcome, and the context was set after the photon entered. But Wheeler pointed out that the same logic applies at any scale, and then he scaled it to something that makes the laboratory version feel quaint. Suppose the photon comes not from a laboratory source, but from a distant quasar, billions of light years away. On its way to Earth, it passes a galaxy that acts as a gravitational lens, and the galaxy's gravity bends the photon onto two separate paths, curving around opposite sides of the galaxy. Both paths, separated by enormous distances, arrive at a telescope on Earth. The photon has been traveling for billions of years. The astronomer at the telescope can choose to measure interference, letting both paths combine, or to identify which path was taken. The choice is made right now, in this moment, and according to quantum mechanics, a decision made today appears to determine what a photon did billions of years ago. The gravitational lens version of Wheeler's delayed choice is not a thought experiment about something that might happen. Galaxies bend light. This has been observed and confirmed since Arthur Eddington measured the deflection of starlight during a solar eclipse in 1919. Massive objects curve space-time, and photons follow those curves. When a galaxy sits between Earth and a more distant source, The galaxy's gravity creates multiple images as photons travel different curved paths around the lensing mass and converge on the same telescope. Somewhere in the night sky right now, photons from distant quasars are being split by intervening galaxies. Those photons have been traveling their two curved paths for millions or billions of years. Astronomers are pointing telescopes at them and deciding, in this very moment, what to measure. The quantum mechanical prediction does not waver. Whether the photon behaves as a wave producing interference or as a particle taking a definite path should match whatever the astronomer decides to measure, regardless of how long the photon has been traveling. A photon leaves a quasar millions of light years away, splits around a galaxy, and travels those two separate paths for millions of years. Species evolve and vanish on Earth. Continents shift. The photon keeps traveling. Then it arrives at a telescope, and the astronomer at the controls decides, in that moment, whether to look for interference or to determine which path was taken, and the photon obeys. The standard interpretation is precise. The photon never had a definite path. There was no point in those millions of years where it committed to the left path or the right one. The question had no answer. The measurement creates the answer. There is no past fact being changed. Because there was no past fact, that is the careful, technically correct way to say it. But it leaves a question about what the word past means at all. If a photon traveling for millions of years has no definite path until the moment of detection, and if the conditions of detection determine which kind of history it will have had, then the past is not a fixed record. In some limited but real sense, what the photon did is determined by measurements made in the present. Wheeler described the universe as participatory. Observations do not simply reveal a pre-existing reality. They participate in bringing definite outcomes into existence. Most physicists find this language too strong. They prefer to say the quantum state was undefined, not that the universe was incomplete. But the experimental results do not care about the language. And if the history of a single photon can remain undetermined for billions of years, a related question was already circling. If two photons share a quantum state and are measured far apart, what happens between them? That question was waiting in a paper Einstein wrote in 1935. It took 30 years for anyone to find a way to answer it. Albert Einstein spent the last 20 years of his life fighting quantum mechanics. He did not dismiss it. He understood it better than almost anyone. He fought it precisely because he understood it, because he had looked at what it implied and found the implication unacceptable. The core of his objection came in a paper he published in 1935 with two colleagues, Boris Podolsky and Nathan Rosen. The paper described a thought experiment designed to show that quantum mechanics, taken at face value, described something that could not possibly be real. The setup involved two particles that had interacted and become entangled. In quantum mechanics, an entangled pair shares a single quantum state. Their properties are correlated in a way that no classical system can produce. Measure one particle's spin along a given axis, and you instantly know the spin of the other particle along that axis, no matter how far apart they are. Quantum mechanics describes this correlation not as a hidden pre-existing agreement between the particles, but as a genuinely undetermined state that becomes definite only at the moment of measurement. Einstein said this was absurd. If measuring one particle instantly determines the state of the other, one of two things must be true. Either the particles are sending signals to each other faster than light, violating everything special relativity had established about cause and effect, or the particles always had those definite states, hidden inside them from the moment they separated, and quantum mechanics simply failed to describe those hidden states. The correlation was pre-existing. Quantum mechanics was incomplete. He called the alternative the idea that one particle could instantly influence another across any distance, spooky action at a distance, and he meant the phrase as a criticism. Nature did not work that way. It could not. Erwin Schrödinger read Einstein's paper and responded with one of his own, coining in that same year the word that would define the field. He called the phenomenon entanglement, a word capturing the idea of two quantum states that cannot be described independently of each other. He was not endorsing it as a feature. He was naming the thing Einstein had identified as the problem. For the next 3 decades, the debate remained philosophical. Both sides had arguments. Neither had a decisive test. Einstein's hidden variables could not be ruled out just by writing down the quantum equations. Whether correlations were pre-existing or created at measurement looked, on the surface, like a question about interpretation rather than experiment. Then, a physicist in Geneva picked up the problem and turned it into something you could test with apparatus you could actually build. The key insight was shockingly elegant. If Einstein was right, if hidden variables determined outcomes in advance, then the correlations between entangled particles could never exceed a specific mathematical bound. If quantum mechanics was right, the correlations would exceed that bound. The two views made different quantitative predictions. That derivation, published in 1964, is arguably the most important theorem in the history of physics. John Bell was an Irish physicist working at the European Nuclear Research Facility in Geneva. Most of his colleagues considered the foundations of quantum mechanics a philosophical distraction from practical work. Bell disagreed. He thought the question of whether quantum mechanics was complete mattered, and in 1964 he found a way to settle it. Bell's insight was this: if particles carry hidden instructions from the moment of their creation, those instructions have to be logically consistent. A particle cannot carry rules for spin, measured horizontally, and spin measured at a slight angle, and spin measured at a greater angle, without those rules obeying certain constraints. Specifically, the correlations between two particles measured at different angles can only be so strong. A strict mathematical bound exists on how correlated their outcomes can be if those outcomes were determined by any local set of hidden variables. Bell derived that bound. He wrote it as an inequality, a specific combination of correlation measurements that any local hidden variable theory must satisfy. The correlations can take many values depending on how the detectors are oriented, but when combined in the specific way Bell prescribed, the total could never exceed a certain number if hidden variables were real. Quantum mechanics predicted something different. For entangled particles, the quantum correlations violate Bell's inequality. The predictions are cleanly separated. Run the experiment and the correlations exceed Bell's bound, and hidden variables are ruled out. Stay within the bound, and quantum mechanics needs revision. Consider what this means: the question of whether reality has definite properties before you look at it. The question that Bohr and Einstein argued about for decades with thought experiments and mutual incomprehension had become a question you could answer by building a machine, firing photons, and recording numbers. The most abstract metaphysical disagreement in 20th century science had been converted into an arithmetic test. Bell published his result and then waited. The technology required to run the experiment, specifically the ability to produce entangled photon pairs and detect their polarizations quickly and reliably, was not yet available in 1964, but the prediction was clear. Over the next decade, the instruments caught up. The first experimental test was performed by John Clauser and Stuart Friedman at Berkeley in 1972. They used entangled photons produced from calcium atoms and measured their polarizations. The results violated Bell's inequality. Quantum mechanics appeared to be right, but the experiment had weaknesses. The detectors were not perfectly efficient. The measurement angles were fixed before the photons were created. Determined critics could find technical escape routes. Over the next decade, a physicist in Paris rebuilt the experiment from the ground up, closed every escape route one by one, and produced a result that was hard to argue with. The data from that Paris laboratory hit the physics community like the closing of a door that had been open for 30 years. Alain Aspect was working at the University of Paris Sud in the early 1980s and the central challenge his experiment faced was a loophole that no one had closed. Clauser and Friedman had produced strong evidence against hidden variables, but their measurement settings had been fixed before the photons were created. A determined skeptic could argue that some unknown mechanism had used that fixed setup to pre-program the correlations. The particles and the detectors were in the same region of space during preparation. Any local physical process had plenty of opportunity to coordinate them. Aspect's solution was the fast switch. He built an apparatus where the measurement settings, the detector orientations, were not decided until after the entangled photons were already in flight. The photons traveled about 20 feet from where they were created to where they were measured. The settings switched in a time shorter than it would take light to travel from one detector to the other. At the moment the setting was chosen, the other detector was too far away to have received any signal about that choice. In 1982, Aspect and his colleagues published the result. The photon correlations violated Bell's inequality. The violation was large and clean, far beyond what chance could produce. Hidden variables, local ones, could not have coordinated the results. There was no time for a signal to travel from one side of the experiment to the other. Whatever the photons were doing, they were doing it in a way that no local mechanism could explain. The result was striking. But the physics community is not given to sudden unanimity. Scientists who disagreed began searching for technical loopholes. Aspect's detectors were not perfectly efficient. Perhaps the detected photons were a biased sample. Perhaps the true correlations, including all the undetected photons, were weaker within Bell's bound. This was called the detection loophole, and it was real. Aspect's experiment could not close it. There was also the freedom of choice loophole. Perhaps the switches generating the random settings were not truly random, or perhaps some pre-existing physical process had influenced both the switch settings and the particle properties through some shared common cause in the past. These escape routes required increasingly elaborate assumptions to maintain, but they were logically coherent, and the physics community took them seriously. A claim as consequential as "the universe has no local hidden variables" demanded scrutiny proportional to its weight. Aspect's experiments did something permanent, though. They moved the question from philosophical debate into precision measurement. Over the next 30 years, an international community of physicists built progressively more precise versions of the experiment, closing loopholes one by one. Then, in 2015, 3 groups at 3 separate institutions closed all the significant loopholes simultaneously. The 3 groups worked independently. One was at Delft University of Technology in the Netherlands, where the entangled particles were placed roughly 3/4 of a mile apart. One was at Vienna, from Anton Zeilinger's group. One was at the National Institute of Standards and Technology in Boulder, Colorado. All 3 published their results in 2015, within months of each other, and all 3 reached the same conclusion. Bell's inequality was violated. Local hidden variables were definitively ruled out. The results were loophole-free. The Delft experiment used electrons, with detection events separated far enough in space that no signal traveling at or below the speed of light could have traveled between the 2 measurements in time. The Vienna and Boulder experiments used entangled photon pairs with detector efficiency high enough to close the statistical escape route that had troubled Aspect's original tests. Together, the 3 experiments eliminated every known technical loophole simultaneously. What had been ruled out requires careful statement. The formal claim is the death of local realism. Local realism combines 2 assumptions that most people consider obvious. The first is locality. An event in one place cannot instantly influence an event in a distant place. The second is realism. Particles have definite properties before those properties are measured, and measurement reveals a pre-existing value rather than creating one. Bell's theorem says you cannot have both. The correlations between entangled photons are too strong to be explained by any theory that assumes both. The experiments confirm that the correlations really are that strong. Something has to give. Most physicists drop local realism but maintain that quantum mechanics does not allow faster-than-light signaling because the correlations cannot be used to send information between the measurement sites. The non-locality is statistical, appearing only when you compare results from both sides. No usable signal passes. In 2022, the Nobel Prize in Physics went to Alan Aspect, John Clauser, and Anton Zeilinger for experiments with entangled photons, establishing the violation of Bell inequalities and pioneering quantum information science. The Nobel Committee's summary stated that the experiments had shown the universe to be not locally real. That phrase is the most important statement the Nobel Committee has ever made about the nature of the physical world. Photons are the particles through which this was demonstrated. 2 photons, entangled in a lab, sent to distant detectors, measured at randomly chosen angles, producing correlations that no physical story about pre-existing local properties can account for. Whatever the universe consists of at the level where photons live, it is something stranger than anything classical physics imagined. That strangeness does not begin with entanglement. It goes deeper, into what a photon is when it is not shared with a partner. Start with the simplest fact, the one that feels least strange until you press it. A photon has no mass, and yet it can push a spacecraft. Rest mass is the mass a particle has when it is sitting still. It is the quantity that appears in every equation of classical mechanics, the fundamental measure of how hard something is to move. Almost every particle in the universe has rest mass. Electrons have rest mass. Protons have rest mass. Even the smallest atom has rest mass. The photon has none, not a small amount. Not an amount too tiny to measure. Exactly 0. As far as any experiment has ever been able to determine, and the standard model of particle physics predicts exactly 0 from mathematical requirements. For electromagnetism to work the way it does, for electric and magnetic fields to have the properties they have, the photon must be massless. Any mass at all, no matter how small, would break the symmetry that holds the entire theory together. The consequence of 0 rest mass is absolute. A photon can never be at rest. It has no rest frame. Accelerate yourself to 99% of the speed of light and aim a detector at an oncoming beam of light, and that light will still arrive at the full speed of light. This is one of the foundational results of special relativity, confirmed in every configuration of experiment for over a century. Massless particles always travel at exactly that speed because that is the only speed the equations of relativity permit them to travel. Any other speed would require a rest frame, and there is no rest frame for a particle with 0 mass. So the photon has no mass, cannot be at rest, cannot slow down. How does it push things? The answer is momentum. In classical mechanics, momentum is mass multiplied by velocity. An object with 0 mass has 0 momentum by that formula. But classical mechanics is an approximation valid only at speeds far below the speed of light. The full relativistic equation gives, for a massless particle, momentum equal to energy divided by the speed of light. A photon carries energy, it therefore carries momentum. When it is absorbed by an object, that momentum transfers. Solar sails demonstrate this directly. A solar sail is a spacecraft with no engine and no fuel, propelled entirely by the pressure of light from our star. They have been built and tested. The force is tiny, only a few millionths of a newton per square yard of sail at the distance of Earth from our star. But it is real and measurable. A sufficiently large sail, given enough time, can accelerate a spacecraft to significant speeds. The pressure of light is the pressure of photon momentum transferring to matter, collision by collision, massless particles delivering a genuine physical push. This works because the photon, despite having no mass, is not nothing. Its energy is real. Its momentum is real. The connection between energy and momentum for a massless particle is given by one of the simplest equations in physics. Energy equals momentum multiplied by the speed of light. Photons are made of pure energy and pure momentum in exact proportion, without any rest mass between them, and this leads directly to the strangest property the photon possesses, the one that makes it genuinely unlike any other thing in the universe. For a photon, time does not pass. Every clock in the universe obeys the same rule. Move faster and time slows down. This is not a hypothesis or a working model. It has been measured in particle accelerators, in the orbits of satellites whose onboard clocks must be corrected to stay synchronized with ground stations, in the decay rates of muons created by cosmic rays high in the atmosphere, particles that would normally disintegrate before reaching the ground but survive the full descent because their clocks run slow in flight. The evidence is unambiguous. Follow that rule to its natural end and something remarkable emerges. Take a particle with mass and accelerate it to 99% of the speed of light. At that speed, its clock ticks roughly 7 times slower than a stationary one. Push to 99.9%, and the clock runs about 22 times slower still. The closer you approach the speed of light, the more extreme the dilation becomes. At the limit itself, time would stop entirely. The photon travels at exactly that limit. It has no choice. A massless particle cannot travel at any other speed. The equations of relativity allow only one value for a zero-mass particle in vacuum, and that value is the speed of light. So the time dilation that slows and ultimately halts a clock applies to the photon completely. A photon's clock does not tick slowly. It does not tick at all. Physicists describe this precisely. Every path through space-time carries a quantity called the space-time interval, a combination of distance traveled and time elapsed that produces a single number. For massive objects, this number is always positive. For a photon traveling through empty space, the space-time interval is exactly 0. The path is called a null geodesic, a path through space-time where the interval vanishes, and it carries a consequence that requires a moment to absorb. A photon emitted from a galaxy 13 billion light-years away experiences 0 elapsed time on its way to your retina. 0. That galaxy fired the photon. Your eye caught it. Those two events are separated by 13 billion years from the perspective of every massive observer in the universe. From the standpoint of the space-time geometry describing the photon, emission and absorption are the same event. Here is where the precision matters. The photon has no reference frame. You cannot transform yourself into a frame that travels alongside a photon, because doing so would require infinite energy, and the mathematics fails before you get there. Asking what the photon experiences on its journey is a category error in the way that asking what the color blue smells like is a category error. The question has grammatical shape, but no valid answer. What is true is this. The photon's proper time is 0. The quantity that measures elapsed time along its world line returns 0. Between emission and absorption, from the geometry of spacetime's own accounting, there is no duration. The 13 billion years that passed for everything else, the galaxies spinning, the stars forming and exploding, the whole long unfolding of the universe between the moment that photon left its source and the moment it reached your eye, all of it happened in a gap that the photon, by the laws of physics, cannot have inhabited. The photon sits outside of time, and that raises a question more immediate and harder to dismiss. If the photon occupies no time on its journey, where is it during that journey? Where, precisely, is a photon at any given moment? The answer is one of the most genuinely strange things in all of physics. Locating a particle seems simple. Electrons have positions. You can, in principle, narrow down where an electron is to a very precise location, though doing so disturbs its momentum. Protons have positions. Every massive particle in quantum mechanics comes equipped with what mathematicians call a position operator, a mathematical object that, when applied to the particle's quantum state, returns a probability distribution for where the particle is likely to be found. The photon has no such operator. This is not a gap in current technology or a limitation physicists hope to eventually close. A theorem derived in 1949 by Theodore Newton and Eugene Wigner showed that for massless particles with spin 1, the standard quantum mechanical position operator simply does not exist. You cannot write down a consistent mathematical object for photon position that satisfies the basic requirements such an operator would need. The mathematics fails for reasons built into the structure of relativistic quantum mechanics itself. What does this mean in practice? When a photon is detected, it is absorbed at a single point. The detector clicks. The detection is local and definite. A photographic grain darkens at a precise spot on a film. An atom in a detector registers a specific energy deposit at a specific location. So photons clearly do something at a point. The problem is in the state before detection. An electron has a wave function that can be narrow or wide, but the wave function is always, in principle, a proper probability distribution for position. The photon's quantum state spreads through space differently. Photons can be distributed across a beam in a way that has no clean single particle position interpretation. The photon is not somewhere in that beam. The photon's state is the beam. Go further still. Entangled photons in a quantum eraser experiment, or the photons passing through the double slit, do not have paths. They do not have trajectories. The delayed choice experiments confirmed that asking which path a photon took before measurement defines the answer is a question with no correct response. The path does not exist before the measurement. Position is even more fundamental than path. If a photon has no trajectory, it has no sequence of positions, and the question of where it is at any specific moment is meaningless in a very precise sense. The photon smears. It fills space as a quantum state, extended and undefined, and when it interacts with matter, it deposits its energy and momentum at a single point. The transition from everywhere in the beam to here, exactly here, is what measurement does. Before that moment, asking for the location is asking for something the photon is not equipped to have. This connects to everything that came before. The double-slit interference pattern, the quantum eraser, the delayed choice results, the Bell violations, all of them depend on the photon being genuinely delocalized before detection. If photons had definite positions before being measured, the interference patterns could not form. The smear is not a failure of instruments. It is what allows a single photon to pass through two slits simultaneously and interfere with itself. Definiteness and interference are incompatible, and the photon maintains that incompatibility right up until something forces a choice. So the photon has no mass, no time, and no position. The properties we typically use to describe a physical object, its location, its trajectory, its clock, are all absent, and yet it is the most abundant particle in the observable universe. What, then, is it made of? The deepest answer physics has ever produced for what a photon is made of is this: nothing. That requires unpacking. Quantum field theory is the most fundamental framework physics currently has. It underpins the standard model of particles, explains the behavior of every known force except gravity, and makes predictions so precise that testing them is one of the central achievements of modern science. At the heart of quantum field theory is a simple and radical claim. The basic ingredients of the universe are fields. Fields, not particles. A field is a mathematical object that has a value at every point in space and at every moment in time. The electromagnetic field exists everywhere in the universe simultaneously. Every point in the cosmos, including the empty space between galaxies, between atoms, between the nuclei of atoms and their orbiting electrons, carries a value of the electromagnetic field. That field is not made of anything more fundamental. The field is the fundamental ingredient. Everything else is made of it. A photon, in this picture, is an excitation of the electromagnetic field. When the field at some location is disturbed, when charged matter accelerates and causes the field to ripple, that ripple propagates outward as a quantized wave packet. The quantization is Planck's legacy. The ripple carries energy only in discrete amounts, each proportional to the frequency of the oscillation. That discrete chunk of field energy is what we call a photon. Think of the field as the surface of a deep lake extending infinitely in all directions. At rest, the surface is flat and silent. Disturb it, and a wave radiates outward. The wave is not a thing you added to the lake. It is a pattern of the lake itself, a temporary structure in the thing that was already there. The photon is that wave. It is a ripple in a field that fills all of space and was already present before the photon existed. Steven Weinberg, one of the architects of the Standard Model, stated it plainly: the basic ingredients of nature are fields. Particles are derivative phenomena. What we call a particle is a particular kind of behavior exhibited by a field under particular conditions. The electron is a ripple in the electron field. The photon is a ripple in the electromagnetic field. The particle is real in the sense that the ripple is real. But there is no small ball at the center. There is only the field. This resolves the wave-particle duality that troubled physics for 2 centuries. The photon was never a wave or a particle in the classical sense. It was always a quantum excitation of a field, something that spreads through space like a wave during propagation and deposits energy at a single point like a particle during absorption. Both behaviors follow from the same underlying object. The duality was a clue that pointed here. The electromagnetic field exists throughout all space, always. It existed before the star that produced the photon now entering your eye. It will exist after the photon is absorbed and disappears. The photon is born from the field when energy is added to it, and it returns to the field when that energy is deposited elsewhere. Between emission and absorption, the photon is the field in motion. Now, here is the thing that should stop you cold. The electromagnetic field exists everywhere. And even in the regions where no real photons are present, the field is still doing something. The question is what it is doing, and the answer challenges every intuition you have about empty space. The force between 2 electrons repelling each other crosses space. That much is obvious from any basic physics course. What is less obvious, and stranger than almost anything in this story so far, is how the force is actually carried. In quantum electrodynamics, the force between charged particles is not transmitted by invisible pressure or pulled by invisible strings. It is carried by photons. Photons that no detector will ever catch. These are called virtual photons, and they are where quantum field theory begins to look genuinely bizarre. A real photon is created, travels some distance, and is absorbed. It satisfies a specific relationship between its energy and its momentum, a relationship that defines what counts as a real particle of light. A virtual photon does not satisfy that relationship. Its energy and momentum can take values that a real photon cannot have. It exists only as a transient, borrowed disturbance in the electromagnetic field, flaring into existence and vanishing before any measurement could detect it. It is real enough to carry force. It is not real enough to be caught. When an electron approaches another electron, the 2 exchange virtual photons. The exchange carries momentum from one to the other and produces the repulsion we observe. At every moment, in every atom, every molecule, every chemical bond, the electromagnetic force, mediating the interactions of charged matter, is being carried by virtual photons cycling between charges too rapidly to count. The theory describing all of this, quantum electrodynamics, was built in the 1940s by 3 physicists working independently. Richard Feynman in the United States, Julian Schwinger also in the United States, and Shinichiro Tominaga in Japan, who had arrived at the same conclusions entirely separately during the war years, isolated from the physics community in the West. All 3 shared the Nobel Prize in Physics in 1965. Freeman Dyson, who was not included in the prize, played a crucial role in showing that all three formulations were mathematically equivalent. Feynman invented a way to visualize the calculations by drawing diagrams, where lines represent particles and wavy lines represent photons. Each diagram corresponds to a mathematical term. You sum up all possible diagrams to get the full answer. The simplest interaction between two electrons involves a single virtual photon. Then there are diagrams with 2 photons, 3 photons, loops within loops. Each more complicated diagram contributes a smaller correction to the answer, but all of them contribute something. The precision this achieves is unprecedented in science. The magnetic behavior of an electron can be calculated in quantum electrodynamics using these diagrams. The result, when compared to experiment, matches to 12 decimal places. That level of agreement has no parallel anywhere else in the history of physics. Quantum electrodynamics is the most precisely verified theory ever constructed, and at its heart is the concept that force is carried by photons that exist briefly and vanish before they can be observed. The virtual photons between electrons are not traveling across empty space. They are fluctuations of the electromagnetic field already filling the space between the charges. The field is there. The charges disturb it. The disturbance propagates. Force results. And if the field is already everywhere, what is it doing in the places where there are no charges at all? What is happening in space that contains absolutely nothing? The answer reveals that space is full of something invisible. Remove everything from a region of space. Every atom, every photon, every electron, every particle of any kind, evacuate it completely. Drop it to the lowest temperature physics allows, absolute zero, where all thermal motion stops. According to classical physics, you would be left with nothing, absolute stillness, a void. Quantum mechanics disagrees. The electromagnetic field exists everywhere, including in that evacuated region. A quantum field cannot simply sit at zero. The uncertainty principle, which governs every quantum system, forbids exact rest. The more precisely a field is pinned to zero energy, the more wildly its value fluctuates. In the quantum vacuum, the electromagnetic field seethes constantly with fluctuations, little disturbances that pop up and vanish across every point of space at every moment. These are called vacuum fluctuations, and they are not metaphorical. They are real, and they have measurable consequences. The first sign appeared in 1947 when a physicist named Willis Lamb measured the energy levels of hydrogen with extraordinary precision and found a tiny discrepancy. 2 energy states of hydrogen that classical quantum mechanics said should be identical were not identical. They differed by a small but definite amount, a separation that became known as the Lamb shift. The explanation came from Feynman and Schwinger almost immediately. The electron in a hydrogen atom is not sitting quietly in its energy level. It is being constantly buffeted by the vacuum fluctuations of the electromagnetic field surrounding it. These invisible fluctuations give the electron a tiny extra jiggle, and that jiggle shifts the energy levels by exactly the amount Lamb had measured. The quantum vacuum was not merely theoretical. It had nudged a hydrogen atom and left a fingerprint. The same vacuum fluctuations produce a correction to the electron's magnetic moment, the anomalous term that quantum electrodynamics predicts to 12 decimal places. Every one of those extra decimal places requires accounting for the vacuum doing something. The most precise calculation in science is, at its core, a calculation about what empty space is doing to matter. Think about what this means for light. The electromagnetic field exists everywhere, and even in regions with no real photons, that field is alive with short-lived disturbances that continuously arise and fade. Virtual photon pairs wink in and out of existence across all of space at all times. The vacuum is not a background against which things happen. It is an active participant in every quantum process. Some of those virtual photons, if they are interrupted before they can cancel out, if the geometry of space constrains which fluctuations are possible, can be forced to leave a mark on the physical world. The vacuum has energy. Zero-point energy is the term physicists use for the irreducible energy of the electromagnetic field in its ground state, the energy it has even at absolute zero. This energy cannot be extracted and used to run an engine. But it is real in the sense that any physical quantity is real. It participates in interactions, it affects measurements, and it exerts forces. One of those forces was predicted in 1948 by a Dutch physicist, and it took nearly 50 years for technology to measure it. When someone finally measured it, the result matched the prediction almost exactly, something from nothing, pulling two objects together. The experiment sounds like it should produce nothing. Two flat metal plates, perfectly conducting, placed very close together in a perfect vacuum. No charge applied, no magnetic field, no thermal radiation, nothing touching them, nothing pulling them, nothing pushing them. In classical physics, two neutral objects in vacuum have no reason to interact. They sit there. That is all. Place them close enough together, and they will move toward each other. This is the Casimir effect, predicted by Hendrik Casimir in 1948, measured for the first time with sufficient precision by Steve Lamoureux in 1997, and confirmed by multiple experiments since. The force is real. The mechanism is the quantum vacuum. Here is how it works. Outside the plates, the electromagnetic field vacuum fluctuations fill space in all their variety. Fluctuations of every wavelength, every orientation, every frequency pop in and out of existence throughout the surrounding space. Between the plates, the geometry is different. The plates are conducting, and conducting boundaries impose constraints on the electromagnetic field. A virtual photon with a wavelength longer than the gap between the plates cannot fit. Those modes are suppressed inside the cavity. Outside, no such restriction applies. The result is a difference in vacuum energy. Inside the cavity, fewer modes of the electromagnetic field contribute to the vacuum fluctuations. Outside, the full set is present. The pressure from outside is greater than the pressure from inside. The plates are pushed together by the difference. At a separation of 1/1,000,000th of a meter, for plates about 1 centimeter on a side, the force amounts to roughly 1/10,000,000th of a newton. That is extraordinarily faint, comparable to the weight of a water droplet smaller than a grain of sand. Building equipment sensitive enough to measure it required decades of instrumentation development. When Lamoureux published his measurement, the agreement with Casimir's prediction was within a few percent, close enough to confirm the basic mechanism. Subsequent experiments improved precision significantly. At very small separations, the force can be large enough to matter for practical engineering. Tiny mechanical devices, operating at nanometer scales, where surfaces are separated by only a few hundred atoms, can be affected by Casimir forces in ways that influence their function. What started as a philosophical curiosity about vacuum physics has become a real consideration in the design of small machines. The Casimir effect is proof that the vacuum pushes. The absence of something, the modes that cannot fit between the plates, creates a net force by making the outside more active than the inside. Physics, at its deepest level, is sometimes more about what is not there than what is. Now the picture is complete enough to ask something that seemed impossible for decades. If the electromagnetic field fills all of space, if photons are excitations of that field, if the vacuum seethes with virtual photons even where no real photons exist, what happens when you force real photons into a state where they all share the same quantum identity? What happens when you push light into a condition where enormous numbers of photons are all doing exactly the same thing at the same time? In ordinary circumstances, photons resist this. They vanish before they can accumulate. Getting photons to pile up into a single quantum state, the way cold atoms do in a Bose-Einstein condensate, was thought to be essentially impossible. A team in Germany decided to press the question. Bose-Einstein condensation is what happens when a collection of identical bosons, particles that obey the quantum rules allowing many of them to pile into the same state, is cooled to the point where thermal energy can no longer kick them out of the ground state. One by one, they collect there, indistinguishable from each other, until the whole ensemble behaves as a single quantum object. Einstein and Satyendra Nath Bose predicted the effect in the 1920s. The first observation, in a gas of rubidium atoms in 1995, earned the Nobel Prize in Physics in 2001. Photons are bosons. They obey exactly the statistical rules that allow bosons to condense. A photon condensate, a single quantum state occupied by a vast number of photons all behaving as one, should in principle be possible. For decades, physicists considered it effectively impossible. The reason was specific and seemed insurmountable. When you cool a gas of atoms to make a condensate, the atoms stay around. They do not disappear. Photons behave differently. As a system of photons cools, the photons do not slow down. They simply vanish, absorbed by the walls of whatever container holds them. Their number is not conserved. A cavity full of photons at low temperature does not condense, because by the time the temperature is low enough to favor condensation, most of the photons are gone. The team at the University of Bonn, led by Martin Weitz, solved this by creating a system where photon number was effectively conserved. Their setup used an optical microcavity, two curved mirrors separated by a distance about 1.5 wavelengths of visible light. Inside the cavity, they placed a dye, a material that absorbs photons and re-emits them. When a photon was absorbed by a dye molecule, the dye quickly re-emitted another photon rather than dissipating the energy as heat. The cavity trapped the photons, bouncing them back and forth, while the dye molecules acted as a thermal bath, repeatedly absorbing and re-emitting photons until the photon gas came into thermal equilibrium with the dye at room temperature. Crucially, the curved mirrors gave the trapped photons an effective mass by creating an energy minimum at the center of the cavity. This effective mass gave the photon gas a chemical potential, the mathematical ingredient required for Bose-Einstein condensation to occur. In 2010, published in the journal Nature, the team reported that above a critical photon number of roughly 77,000, the photons condensed. The excess photons poured into the lowest energy state of the cavity, occupying that single mode in overwhelming numbers, becoming indistinguishable from each other. The condensate appeared at room temperature because the effective photon mass was so much smaller than an atomic mass that the critical temperature for condensation shifted enormously upward. A Bose-Einstein condensate of light. Assembled at room temperature, a state where tens of thousands of photons became a single coherent quantum object. The condensate was not a laser. A laser creates coherent light through stimulated emission, which requires population inversion and an input of energy. This condensate formed the way ice crystallizes from water through a thermodynamic phase transition by the quantum statistics of identical bosons running out of anywhere else to go but the ground state. Photons, the restless time-indifferent particles that had been defying classical intuition since Newton's day, had been persuaded to sit still and crowd together into a single quantum identity. But the most extreme environment a photon ever encounters is not a dye-filled microcavity. It is the boundary of a black hole. And what happens there challenges everything. A black hole is the place where physics stops working cleanly. Inside the event horizon, the boundary from which nothing can escape, space-time curves so severely that every path leads toward the center. A photon aimed directly outward from just inside the horizon is still carried inward. The geometry of space-time itself flows the wrong way. Light does not escape. That is the defining feature of the object. Stephen Hawking, in 1974, showed this was almost true. Hawking applied quantum mechanics to the region just outside the event horizon and found something the classical picture had missed entirely. In the quantum vacuum, virtual particle pairs flicker constantly in and out of existence, as we saw a few chapters ago. At every point in space, particle-antiparticle pairs appear and annihilate before they can be detected. Usually the two partners recombine and cancel each other within the brief window allowed by the uncertainty principle. At the edge of a black hole, the geometry intervenes. When a virtual pair appears very close to the event horizon, the intense curvature of space-time can separate the partners before they can recombine. One partner falls inward across the horizon and is consumed. The other escapes outward into space as a real particle. The escaped particle has energy. It has momentum. For the electromagnetic field, this means real photons are emitted from just outside the event horizon at a temperature that depends on the black hole's mass. This is Hawking radiation. The photons emerge at all wavelengths, with a distribution that looks like the glow of a warm object. The temperature is extraordinarily low for any black hole we know of. A black hole with the mass of our star would have a Hawking temperature a fraction of 1/1000th of a degree above absolute zero, far colder than the cosmic microwave background radiation filling the universe. Such radiation would be completely undetectable against the noise of the cosmos. The importance of Hawking radiation is not practical. It is theoretical. These photons carry energy, and that energy comes from the black hole itself. The black hole slowly loses mass. Over timescales far beyond the current age of the universe, the evaporation continues until the black hole is gone. Photons born from quantum effects at the horizon, accumulated over unimaginable stretches of time, dismantle the most indestructible object physics has ever described. The crisis Hawking radiation creates is called the information paradox. When matter falls into a black hole, information about what that matter was, its quantum state, its detailed physical description, seems to be lost. Quantum mechanics insists that information cannot be destroyed. But Hawking radiation appeared to carry only thermal noise, encoding nothing about what fell in. Two of the most powerful frameworks in physics, quantum mechanics and general relativity, were making directly contradictory claims. One of them is wrong, or both are incomplete. This paradox remains unsolved. A photon born at the edge of a black hole sits at the intersection of the three great theories that have never been fully reconciled, and its existence exposes the gap between them. The universe's most extreme objects dissolve into light, and the light carries a question no one has answered. What physics is discovering about photons right now, in laboratories operating today, suggests the question goes even deeper than anyone realized a year ago. In March of 2026, a paper appeared that rewrote what the most routine experiment in quantum optics had been doing all along. Spontaneous parametric downconversion is a process that most quantum optics laboratories have used for decades. Shine a laser through a special crystal and occasionally a single photon splits into two photons, each carrying half the original energy. The two daughter photons emerge, entangled. This is how most of the entangled photon pairs in Bell tests, in quantum cryptography. It is standard, well characterized, familiar to anyone in the field, or so everyone assumed. A team at the University of the Witwatersrand in South Africa, working with colleagues in China, analyzed the orbital angular momentum of those photon pairs in more depth than anyone had attempted before. Orbital angular momentum describes whether a photon's wavefronts spiral as they travel, like a corkscrew of light. Photons can carry this kind of angular momentum in ways that give them specific topological structure. What the team found was nothing like what anyone expected. The entangled pairs were generating hidden structures in 48 dimensions, with over 17,000 distinct topological signatures encoded in the orbital angular momentum alone. These were not exotic laboratory conditions. They appeared in the standard photon pairs that every quantum optics laboratory in the world produces every day. The rich topology had been invisible because no one had looked for it. Professor Andrew Forbes at the University of the Witwatersrand described it as a fundamental discovery. One property of light was sufficient to create this topology. Whereas previous thinking had assumed at least two distinct properties would be needed, the implications for quantum information are significant. Topological structures are robust against noise. Information encoded topologically tends to survive disturbances that would destroy conventional quantum information. Those 17,000 signatures, hidden inside ordinary entangled photon pairs, represent potential information channels of a density that existing quantum communication protocols do not come close to using. Alongside this discovery, two separate research groups in late 2025 demonstrated quantum teleportation between different quantum dot sources, a milestone the field had been working toward for years. A quantum dot is a tiny semiconductor structure that emits single photons on demand. Previous teleportation experiments had used photons from the same source. Using two different quantum dot sources connected by optical fiber and linked by precise synchronization, the groups achieved the faithful transfer of a quantum state at fidelities exceeding 80%, well above the limit achievable by any classical system. At Stanford, a device using a material called molybdenum diselenide accomplished quantum entanglement between a photon spin and an electron spin at room temperature without cryogenic cooling. Published in December of 2025, this result removed one of the central engineering obstacles separating quantum communication technology from everyday practical use. The photon is not a solved problem. A laboratory experiment so familiar that most quantum physicists have run it hundreds of times was concealing 48 dimensions of structure that no one suspected. The frontier is not only in the exotic, it is hiding inside the ordinary. And all of this, every discovery laid out in this story, every experiment from young slits to topological photon states, is building toward one final question. The same question that has been running since the opening chapter, the one that has never been cleanly answered. What is a photon, really? The reason the photon matters practically, beyond everything strange and fundamental laid out in the chapters before this, comes down to one property that no other particle has. A photon travels at the speed of light while maintaining quantum properties. An electron can carry quantum information, but it is massive and slow, and its quantum state degrades rapidly in any conducting medium. Atoms store quantum information beautifully, but they cannot travel far. The photon moves, fast and lightly, through optical fiber and through empty space, carrying its quantum state intact over long distances. This makes the photon the only viable carrier of a quantum internet. A quantum internet is not a faster version of the internet already in use. It is a fundamentally different kind of network, one whose security is guaranteed by the laws of physics rather than mathematical difficulty. Current internet security is based on problems that are extremely hard to solve computationally. A sufficiently powerful quantum computer, a type of device now being built, could in principle crack those protections. Quantum cryptography using photons offers something different. Its security comes from a physical fact. Any attempt to eavesdrop on a quantum channel disturbs the photons being measured, and that disturbance is detectable. An eavesdropper cannot read a quantum message without leaving evidence. In July of 2024, a research team achieved high-rate quantum key distribution using a single quantum dot photon source, sending individual photons down a deployed fiber link with attenuation of roughly 25.5 decibels, comparable to the losses in a real urban fiber network, and maintained secure key generation continuously for over 35 hours. This was proof that single photon quantum cryptography functions at real-world distances and timescales. In September of 2025, Purdue University demonstrated a functioning quantum network distributing entangled photons between 3 separate laboratories. The photons traveled through standard optical fiber connecting different rooms. Entanglement was verified between nodes. The network was small, confined to a single building, but the principle was demonstrated in hardware that could be scaled. That same year, the Stanford device pointed towards something even more consequential. One of the engineering barriers to practical quantum communication has been the requirement for cryogenic cooling. Room temperature operation opened the possibility of quantum devices embedded in ordinary electronics, potentially small enough to fit in a handheld device. The photon connects the abstract to the concrete. The uncertainty principle, complementarity, entanglement, the field beneath everything. These are not curiosities confined to the philosophy of physics. They are the engineering principles of the next generation of communication. The quantum computer that will eventually threaten current cryptography is a real machine being assembled right now. The quantum cryptography that photons enable is the response to that threat. All of this rests on properties of the photon that took more than a century to understand and that remain, in the deepest sense, not fully understood even now. The question that opened this story, the one asked when you were standing in a room full of light you had never thought to question, has traveled through 2,000 years of wrong answers, through slits and delays, and entangled particles and vacuum forces and condensed light. It has arrived at a final moment that refuses to close cleanly. Because the honest answer to what a photon is, after all of that, is both more and less satisfying than anyone hoped. Tomorrow morning you will open your eyes and photons will pour in. 100 billion of them passing through the top of your skull every second, just as this story told you when it began. You will see the ceiling, the light from a window, the slow resolution of the room out of darkness. And you will be using something that the most rigorous scientific framework ever built cannot fully describe. Einstein, who gave the photon to science in 1905, who built quantum theory alongside it through 5 decades of argument and mathematics, said near the end of his life that every fool thinks they know what a photon is, and every fool is mistaken. We have better tools now than Einstein had. Quantum field theory. Bell tests verified to 12 significant figures. Delayed choice experiments with photons that traveled billions of light years before an astronomer decided what to measure. Bose-Einstein condensates of light assembled at room temperature. Virtual photons confirmed by measurements agreeing with theory at 12 decimal places. 48 dimensions of topology hidden inside the most routine setup in quantum optics. The science has advanced immeasurably since Einstein's confession, and yet, the photon is a quantized excitation of the electromagnetic field. That much is settled. It has zero mass, zero proper time. No position before detection, no definite path before measurement. Spin of 1, 2 polarization states, and momentum equal to its energy divided by the speed of light. These properties are known, measured, confirmed, and used in the engineering of devices operating right now. The mathematical description is extraordinarily precise. What the mathematical description does not tell you is what the electromagnetic field is. The field fills all of space, always. Its vacuum fluctuations push metal plates together in the Casimir effect. Its quantum excitations mediate every electromagnetic force in the universe. Its virtual particles adjust the energy levels of hydrogen to 12 decimal places. The field is one of the most real things physics knows about. And physics has no answer for what the field fundamentally is. What kind of thing exists at every point in space, and yet is not a substance you can point to or a medium you can stir? The measurement problem, which the double slit and the quantum eraser and the Bell tests all illuminate from different angles, remains open. When a photon traveling through 2 slits simultaneously arrives at a detector and produces a click, something happens. The probability wave resolves to a definite outcome. The interference pattern distributed across the whole apparatus concentrates at a single point. Every interpretation of quantum mechanics, from Copenhagen to many worlds to objective collapse, gives a different account of what that moment is. None has been ruled out experimentally. None has achieved consensus. What makes reality definite? Measurement. What is measurement, precisely, at the level that would satisfy a complete physical theory? No one knows. Physics has answered an enormous number of questions since Ibn al-Haytham placed his camera obscura in Cairo around the year 1000 and established that light enters the eye from outside. Newton's particles, Young's waves, Maxwell's fields, Planck's quanta, Einstein's photoelectric photons, Compton's momentum, Bell's inequality, the Nobel Prize of 2022 for the death of local realism. Each answer was real. Each was tested, each moved understanding forward. And the thing that every photon entering every eye in every moment of every waking life carries with it, a tiny package of energy and momentum and spin, traveling at the maximum speed allowed by the structure of space-time itself, is still the most fundamentally mysterious object in a universe full of mysteries. We see with something we do not understand to understand everything else. Science's greatest gift has never been the final answer. It has always been the capacity to sit with the question and know that sitting with it honestly, without pretending to more certainty than the evidence allows, is itself the most extraordinary thing a mind can do. The photon passes through your eye. The world becomes visible. What it was, what it is, what reality looks like in the instant before observation, remains open. That openness is the invitation to keep going.